Well, hi all. It's Rob here. Been quite a while since I've posted on this channel. I've been very busy with lots of other things going on in my life and all sorts of things happening. So I thought I'd get something off my chest. Lots have been going on. I've got a new training course that's actually being written as we speak. It's been going on for some time now, over a year now that we've been sorting this out. But it's going to be based in Uxbridge. And I'm going to be working. We'll set up a kind of subsidiary company of Viper Services Group. It's going to be called Viper Hydronics. And I'll be leading up a lot of the training that's going on in there. And I've got some brand new ideas that I think are pretty good for engineers to kind of learn. But I uh, I never wanted to get anything political or anything like that, but I really felt like I've needed to kind of voice my concerns about the what I see as the complete insanity of our energy policies and our energy situations that we have in this country. As everyone knows, I'm an independent design consultant these days, but I've spent like 45, 46 years as a coalface engineer on the tools, both gas and heat pumps and all sorts of things. I now design purely at home in my little studio here is kind of my day working room. Um, but I really needed to voice some concerns about our energy transition. So I spent probably the last 3 months or so, something like that, researching this and trying to get my facts straight on what is our energy transition. A lot of people have said to me, "Why are you bothering doing this, Rob? Why don't you just stick to doing the maths that you do and the tutorials that you do?" Well, frankly, I don't think there's enough discourse on energy, and we as engineers and we as installers, we're told to design and get the best that we possibly can for our clients. Well, at the moment, with electricity costs the way they are and spiraling out of control, the highest industrial electrical costs at the moment I think in the world. So our businesses are failing. There's people leaving the country left, right, and centre because of the policies that we've got and the cost of living crisis, etc., which all, frankly, could be avoidable. And I just thought I need to kind of voice my opinion here, if anybody's interested. And of course, if they're not, that's completely fine. And please understand, it is purely an opinion. I'm not anti anything. I'm completely agnostic as a designer, as an engineer. And I want to make sure that that is clear. There's also what I'm going to say here in the virtues of different fuel types, etc., etc. I'm not bashing anything at all. I'm pro electrification. I'm pro the energy transition, and I want to just make that 100% clear before we move on. But I hope you enjoy this, and I've certainly learnt a lot in this process, and we'll see how it goes. But I really hope you enjoy it. All right, so let's get into it. Okay, all let's get stuck into it. As I say, I've been working on this now for some time, and it's an opinion I've held for many, many, many years that a lot of you will probably understand and know my sometimes controversial understanding of the world and etc. etc. But again, it's just debate, isn't it? I've called this real world thermodynamics versus the political narrative for kind of fairly obvious reasons, as I've kind of described. But this is my perspective, pretty much, on our energy security challenge as we stand now, and hopefully moving forward. But let's see how we go, and we'll go from there. So, first chapter: energy production illusion, generation versus delivery. I'm not an opponent of progress. But as a heating design consultant with 45 years of hands-on experience in this industry, I've spent nearly half a century watching systems evolve from simple cast iron boilers to the highly sophisticated low temperature technologies we use today, as many of you do. My career has been governed by the unyielding laws of physics, thermodynamics, and fluid dynamics. I need to say this again, as it continues to feel as though our industry is no longer being guided by engineers, but blindly led by political idealism and an incredibly warped version of reality. We are being force-fed a narrative by what I can only describe as idealistic eco-zealotry, a narrative that paints the rapid, mandatory electrification of heat as a flawless, plug-and-play, net zero silver bullet. Today, and in this video, I want to step away from the marketing brochures and dramatic news alerts and look at the raw, unvarnished facts. If we're going to build a sustainable future and maintain energy security, we must do it on a foundation of sound engineering and not mythical assumptions. I would hope people would agree with that. So chapter 1, I called this chapter the energy production illusion. It's generation versus delivery. And we have, so, I mean, let us begin really where the energy begins, and that's at the power station. The public is told that moving from a gas boiler to an electric heat pump instantly slashes carbon emissions to zero. Well, this completely ignores the realities of the wider energy system, and I'll explain. The home boiler baseline, as we sit here. When we burn methane locally in a modern, finely tuned condensing boiler, and we must recognise that there are still over 16 million of them out there right now in the UK that are not set up correctly. This is woeful. We convert chemical energy directly into thermal energy inside the home. So a gas boiler, really well set up, it converts chemical energy directly into thermal energy inside the home. When implemented accurately, it's highly effective, running at a seasonal efficiency of approximately 92%, actually a SCOP of 0.92 when maintained correctly, and this is pretty good. Now we have, unfortunately, a transmission penalty on this. That if we take that exact same cubic metre of methane and burn it at a modern combined cycle gas turbine, a CCGT power station, to generate electricity for a heat pump, the efficiency chain degrades immediately. The power station operates at roughly 50 to 55% efficiency, not the 92% of a well set up boiler. Stepping up that voltage, sending it across the national grid, and then stepping it back down strips away another 7 to 9% in transmission losses. This is huge and is never ever discussed. This gives us a delivered reality. So by the time that energy hits a home's consumer unit, only about 45 to 50% of the original energy from that 1 cubic metre of methane burnt is actually available for the consumer. I don't know if anybody else finds that shocking, but I find that absolutely disgraceful and completely what I've said for many years, that we don't have an energy crisis per se, we have a wastage crisis. So we then get what is called a UK winter crunch. During a common Dunkelflaut, or however you pronounce it in the UK, those freezing windless dark nights, dark winter weeks or even months when solar is non-existent and wind generation drops to near zero, the grid relies pretty much entirely on gas-fired and some remaining nuclear generation. Forcing millions of heat pumps onto the grid during a cold snap doesn't eliminate fossil fuels, it simply shifts the combustion of methane from the kitchen cupboard to a distant power station, running at a massive systemic deficit. I like to think of myself as an efficiency engineer these days, and I'm sorry, but this factual data does not sound very efficient to me. Chapter 2. The dying fleet and our 46-year reality check. This brings us to the current terrifying state of our electrical generation infrastructure. The electrify everything immediately crowd treats the grid as a magical, infinite, green fountain. It is absolutely not, and here are the mathematical and physical reasons as to why. The ageing backbone. The flexible dispatchable backbone of the UK grid consists of CCGT stations built during the dash for cash in the 1990s. The operational life of these plants is 25 to 30 years. More than half of the UK's active gas turbine capacity was built before the turn of the millennium and is rapidly approaching the absolute cliff edge of its commercial and mechanical life. No real action has been taken in that time to replace these crucial energy hubs, regardless of energy source. So this gives us a delusional rollout target. We would be seeing devastating localised blackouts by now if successive governments had indeed achieved their targets of 600,000 heat pumps installed each year. Here in mid-2026, we are only looking at around 300,000 total installed so far, and the majority of those installations, sadly, are extremely poorly executed. Is this a real and productive use of public money, allowing £7,500 for each install of a heat pump under the bus scheme, or the bus grant scheme, to bolster this deluded uptake? I truly and genuinely think not. And again, I'm not bashing heat pumps at all, and I'll come to that in a minute. Let's look at the real scary maths here. With a housing stock of over 28 million homes, dividing that by the 600,000 annual target the government wants means it will take 46.6 years to reach this fabled net zero. Yet no backup plan for our energy security in that time, 4.5 decades, is in place for the bridging infrastructure. My mind sincerely boggles at this, and so should yours. We then have an investment void. A bit of a black hole really, if you like. Because of rigid political targets, private capital refuses to build new reliable gas plants. We are left running a dying fleet on life support. precisely while attempting to multiply at scale our national electrical heating load by huge margins. Nowhere is this danger more acute than in Scotland, and we've already seen blackouts in Scotland. Scotland has systemically shut down its robust dispatchable baseload generation, closing Cockenzie, Longannet and Hunterston B. It claims to be a green powerhouse based on wind, but when a winter high pressure system sits over the country and the wind drops to zero, Scotland's domestic baseload is virtually non-existent. Battery backup for these events is a physical impossibility, as any grid engineer will explain, and indeed that concept has massive ramifications in terms of raw material, production, environmental cost and transport considerations. We then have an interconnector threat. Scotland is forced to rely on importing power from England via interconnectors. If England's own ageing 1990s turbine fleet is straining to power millions of English heat pumps during a nationwide cold snap, there will be no surplus power to send north. Scotland faces a highly critical, credible risk of localised blackouts because you cannot run a modern country on intermittent weather and political prayer. Chapter 3, and this is a big one, it's the silent chemical footprint, the F-gas problem. This has taken me some time to research this, but I was shocked to the core as I found out. So as I said, this is a huge one and something I've been researching for some time. It's the third great myth that vapor compression technology is inherently clean. As engineers, we know that heat pumps are essentially complex chemical plants sitting in residential gardens. We have a reality of leaks here, and this is what really shocked me. While a boiler is a sealed loop of water with its own largely benign potential leaks, a heat pump relies on high pressure fluorinated gases, F-gases. Globally, an estimated 700,000 to 800,000 metric tons of these F-gases escape into the atmosphere every single year through slow leaks, poor maintenance, mechanical vibration, and improper but somewhat out of control decommissioning, as a lot of people will know, and as whistleblowers that I've found within the industry have explained to me. It's really, really quite poor, frankly. And that doesn't even get into the automotive industry of R134 gases, which, you know, they can be 500 grams of gas within an individual vehicle, and how many millions of vehicles do we have? And yet these need to be recommissioned almost every single year. So I haven't even added that into the 800,000 metric tons global. We then get a carbon erasure. So the dominant gas currently used in millions of installed units, which is R410A, has got a global warming potential, GWP, of 2088. That means just one single kilogram of leaked refrigerant does the atmospheric damage of over 2 metric tons of CO2. Policy models completely ignore this, assuming a flawless 0% leak rate. In reality, if a domestic system suffers a single catastrophic circuit failure over its 15-year lifespan, its direct chemical emissions instantly wipe out years, if not all, of its supposed carbon savings. Basic research through UK gas suppliers like BOC shows huge rates of replacement F-gas sales annually. That's just in the UK. While heat pumps are not yet the biggest replacement user, they are incredibly far from this fabled net zero. I'm sorry to say that, but it's true. Next generation bottleneck. While the industry is trying to shift to lower GWT alternatives like propane, which is R290, or even CO2, funnily enough, its high flammability limits the maximum allowable charge size inside a residential property, severely restricting its scalability for larger, older or multi-storey UK homes. Indeed, I've just completed one of the largest R290 heat pump cascade installation projects in the UK, comprising 10 16 kilowatt units side by side and stacked, as you can see here in this image. I'm very proud of this project that I designed, but the legal hoops we had to jump through in order to get permission were incredible, driven primarily by the risk of leakage. So I'm not exaggerating here on leakage potential and realism. I've personally seen major manufacturers' internal production brazing on refrigeration pipework that frankly should never have left the factory. I cannot imagine they ever went through the rigorous individual pressure testing required, let alone proper scrutiny after shipping halfway around the world, with a high likelihood of damage in transit or even installation by unskilled engineers. This is a huge subject and something that many training companies, including what I'm trying to set up, are trying to address, so we can understand exactly what our leakage rates are, whether we can mitigate this and make it a little bit better for future generations, as we say. This brings us on to chapter 4, our installation crisis and the real world data gap. Moving into the property itself, we hit the stark contrast between academic theory and physical installation reality. And this brings us on to what we've all trained about for a long, long time. And still only few of us actually have completed courses and understand this fully. A mass flow versus high temperature. A traditional gas boiler is a high temperature, low mass flow system, typically operating with a delta T temperature difference between flow and return onto an appliance of 15 degrees to 20 degrees centigrade. It can comfortably pump out 70 degrees centigrade water to small, thin radiators, but unless it's balanced correctly, it will return water to the condensing boiler at a temperature well above the dew point of 54 degrees. This turns it into a non-condensing condensing boiler. Since the mandatory inclusion of condensing boilers in the UK homes in 2005, we have utterly failed to ensure their real efficiency, and as said, 16 million of them are still set up incorrectly and don't condense. This is woeful. So the industry deficit. A heat pump is an unforgiving, low-temperature mass flow system, yet sadly only a fraction of installation engineers fully understand how to calculate, design and modify existing systems to extract the efficiency gains crucial to the energy transition's credibility and future public support. I and many colleagues have worked tirelessly in this field for over a decade to help educate designers and installers alike. I can honestly tell you we are currently fighting a losing battle against apathy and engineering professionalism, even though we are fully behind all low temperature training ideas and solutions. The maths are not difficult, but I will say a huge percentage of current training is based on monetary greed and bums on seats as opposed to industry and personal competence. Now, there's going to be people that disagree with me on this, but if you do, put your comments in the comments below and cite some actual real data so we can properly have an open and honest discussion on this, and it is purely just a discussion. This then brings us on to an emitter problem. To deliver the same amount of heat into a room using 25 degree, 35, 45 or even 55 degree flow temperatures, the surface area of the emitters or water volume of underfloor heating circuits must be appropriately increased from old and frankly historical bad guesswork. We thankfully oversized everything years ago as a safety factor and are somewhat reaping those rewards right now. But nonetheless, calculation is imperative. Water has a logarithmic and volumetric relationship with flow temperature, which I will explain in my upcoming training course. The myth that you can simply swap out a combi boiler and hook up a heat pump to existing microbore pipework and standard radiators is an engineering falsehood. Without a complete redesign or at least calculation of predicted flow versus temperature of the properties pipework and emitters to accommodate the higher volumetric flow rates, the heat pumps will short cycle, killing the compressor prematurely and destroying operational efficiency. We haven't yet managed to realise the poor efficiency returns of gas condensing boilers for over 21 years, all due to poor training, government incompetence, impotent regulation, unaccountability, and frankly, sheer installer apathy. So I fail to see how we're going to achieve this with a much more complex system like vapour compression technology, or often quadrupling the flow rate to achieve the same replacement of heat loss. So let's look at the real winter maths. Let's look at the maths that these idealistic zealots avoid. In the dead of British winter, when an outdoor ambient temperature drops to -2 degrees, a heat pump's real-world COP, a coefficient of performance, drops sharply to around 2.5 to 2.9. If our delivered grid electricity is only 48% efficient due to the power station and transmission losses, our overall winter system efficiency drops down to a system COP of just 1.2. And to do the maths there, 0.48 divided by 2.5 equals 1.2. Again, this is not absolute and it will vary, but these are kind of almost worst case scenarios by using our existing CCGT gas turbines. Compared to a properly installed condensing gas boiler operating at 92%, the actual energy saving during peak winter is roughly 30% using a heat pump under those conditions that I just explained, and not the 300 to 400% jump of efficiency gains that the public is promised. To achieve a true 2.5 times efficiency increase over a modern boiler, that heat pump would need to sustain a winter COP of approximately 4.7 or 470%, which currently violates the practical thermodynamic limits of air source technology in freezing conditions. I'm not dismissing heat pump technology in the slightest. I'm simply peeling back the misinformation and glossy buzzwords that have always plagued reality, stifled engineers from doing what we do best, and putting myself firmly on the side of the consumer and the long-term energy security of a sovereign nation. And this brings us on to chapter 5, which is the last chapter. This is the kind of the infrastructure blueprint. We're told that to fix our energy transition, we must build 2 or even 3 parallel energy networks, expanding the electricity grid, maintaining the gas grid, and burying brand new district heating loops. The physical materials, the copper, steel, plastic, concrete, and financial capital required to dig up the entire country represent an astronomical debt that will cost our nation dearly. It will never realistically return the net zero myth banded around right now as if it were scientific fact, especially by the plucked out figure of 2030 or indeed 2050. I've always said science is never, ever, ever settled. Anyone who has dug into this insane decision making of duplicating grids and services under the banner of a national emergency will completely understand how bizarre and bonkers it actually is. There is a far more elegant, pragmatic engineering solution sitting right in front of us, and it's called infrastructure reuse. I want to really kind of drum home this point here, and again, this is my opinion. Most people will know that I'm a nuclear advocate, and I'd like to see that represent and deliver our energy transition over time, because in my opinion, it is the true renewable option that we have. The value of retiring sites. When a 1990s gas turbine reaches the end of its mechanical life, or realistic mechanical life, the site itself remains a structural goldmine. These locations already possess massive high voltage grid connections, substations, pylons, and heavy cooling infrastructure designed to feed gigawatts of power directly into the national grid's transmission spine. They've all passed ridiculous and costly red tape bureaucracy and scrutiny for original permission, and therefore do not represent further burden on an already skint public purse. In any other business model, this current structure would be seen as misappropriation of company, or in this case, country funds. The nuclear alternative. The logical, fiscally responsible path is to build nuclear generation, brand new nuclear generation, specifically advanced pressurized water reactors like the Korean company KEPCO, APR 1400, have successfully achieved at least 8 good installations directly on or alongside these existing retiring gas turbine sites. By doing this, we do not need to reinvent the wheel or rebuild our infrastructure network 3 times over. We simply replace the thermal heat source from gas to nuclear, modify and utilise the heavy grid infrastructure we have already paid for, and deliver clean, reliable, truly renewable as we currently know it, continuous baseload power to the nation without tearing up our streets to lay even 1 new metre of copper cable. So my conclusion, and I call it a call for energy sanity. Guys, heat pumps are a brilliant piece of engineering when deployed in the correct building fabric with the correct pipework and emitters by highly skilled engineers. But they are highly sensitive, low temperature thermodynamic instruments, not a generic plug and play home appliance. We must understand a fundamental truth here. The cheapest and most efficient way of using energy is not to use it at all. The current political narrative is built on a dangerous foundation of myths, that our grid is a magical green fountain, that our 1990s generation infrastructure is immortal, and that we can ignore the physical laws of fluid dynamics inside old and indeed any houses. As an industry, we must stop allowing idealistic policy to outpace physical reality. It is time to bring engineering sanity back to the energy transition and discussion, state the harsh but fair facts plainly, and design our national strategy based on the laws of physics rather than the wishful thinking of idealism or very dangerous misguided political zealotry. Guys, that concludes what I have to say here for the moment. This is obviously going to spur, hopefully, some fairly robust conversation, of which I'm more than happy and more than thick-skinned to take. And again, it is purely just an opinion of something that I hold genuinely close to my chest, and something that I'm quite passionate about. I want us to have a very, very profitable country. I want us to have cheap, reliable, baseload energy that is very, very abundant for everybody. I cannot see another way through this other than to invest in nuclear. But again, I welcome all your thoughts. If you like this video, please subscribe. Please comment, and I will do my best to answer every single comment, depending on the scale of comments on this, because it will be quite controversial, I'm sure. And I hope to see you in future training sessions and future videos that I'm going to do. So many thanks, guys, and see you again. Cheers. Bye bye.